Today we've got a nice problem that was suggested by a viewer. In fact, the viewer good place to stop if you're aware of this person. And while this looks pretty similar to other problems that we solve on the channel from time to time, this one in fact is a lot trickier. And I think everyone will agree to that when we look at the solution. So it's from the 2023 Romanian Masters Math Competition. And the goal is to find all positive integers x and y and prime numbers p satisfying the equation that x cubed plus y cubed is equal to p times xy plus p. So looking at this x cubed plus y cubed really gives me some motivation to use the sum of cubes factorization formula. So that's exactly what we're going to start with. So we've got x cubed plus y cubed is equal to x plus y times x squared minus xy plus y squared. And then looking at that x plus y out front, that gives some motivation to maybe make some sort of substitution for x plus y equals a variable. But in order to motivate that substitution a little bit more, let's rewrite this a little bit. So we've got x plus y. Then I'm going to do something tricky here. So I'm going to write it down first, and then we'll talk through it. So I've got x plus y squared, and then minus 3xy. Now observe, if you do x plus y squared, you pick up a x squared plus y squared plus 2xy, but then subtracting off this 3xy brings us back to this minus xy right here. Okay, and now I think we've fully motivated the substitution that I talked about before. So let's substitute t equals x plus y. But then that tells us that x cubed plus y cubed can be rewritten as t times t squared minus 3xy. So we've got something like that. But then while we're at it, I'm going to do another little calculation with t. This calculation we'll use later. So let's observe that we can square t, and we'll get t squared, which is pretty clearly equal to x squared plus 2xy plus y squared. But then by the arithmetic geometric mean inequality, we know that x squared plus y squared is bigger than or equal to 2xy, meaning this whole thing is bigger than or equal to 4xy. So like I said, that's by the arithmetic geometric mean inequality. So I'll just shorten it like that. Okay. But now what we'll do is take our substitution right here, this x cubed plus y cubed equals t times t squared minus 3xy, and see what our original equation looks like. So our original equation at the moment looks like t times t squared minus 3xy equals p times xy plus p. So observe that now we've got three variables. We have t, p, and then x times y is really kind of like its own variable, although we will leave that as is. So what I'll do now is solve for xy. So observe that we have t cubed minus 3 times t times xy equals p times xy plus p squared. So let's move some things around a little bit. So let's see, we could have a t cubed minus a p squared by subtracting this p squared over is equal to, let's see, 3txy plus p times xy. But we can factor an xy out of this, and we'll have 3t plus p. But we can divide by the appropriate term, and we'll have xy is equal to t cubed minus p squared over 3t plus p. But now let's combine this with the inequality that we have over here. So maybe I'll put a pink star next to this inequality and just note that that's what I'm using here. So let's observe that we have t squared is bigger than or equal to 4 times x times y, but 4 times x times y, given our equation right here, is 4 times t cubed minus p squared all over 3t plus p. So we've got something like that. But now I can cross multiply and I'll have 3t cubed plus t squared p is bigger than or equal to 4t cubed minus 4p squared. So again, that's just a simple rewriting of the inequality that we have over there. But now we can move some things around here and get the following inequality. So we'll have t cubed minus t squared times p. So that's going to be moving this 3t cubed over to the other side, and then this t squared times p to the other side, and then minus 4p squared. And the way that we've done it, all of this is less than or equal to 0. But since we're working over the natural numbers, getting something less than or equal to 0 is going to be meaningful. Sure, we've got minus signs in there, but that's actually okay for our purposes. But what I'll do now is I'll replace this p squared with a p cubed. And if I replace that p squared with a p cubed, my non-strict inequality turns into a strict inequality. So in other words, I know that t cubed minus t squared times p minus 4p cubed is strictly less than 0. And the reason I did that is now I've got a cubed term here, and well, it's not exactly a cubed term there, it's 4 times a cubed term. And in fact, what we can do is factor all of this. It has a little bit of a non-obvious factorization, but if you play around with it enough, you'll see that this is t minus 2 times p, and then times, it'll be t squared plus tp plus 2p squared. So we need that to be less than 0. But let's look at part of that. This second term right here is obviously bigger than 0. That's because all parts of it are natural numbers, which automatically make them bigger than 0. But that means that the other portion of this is got to be less than 0, since the whole thing is negative. But if that's less than 0, then that gives us the inequality between t and p, which is t is less than 2 times p. Okay, so now let's start from that inequality and move forward. So before we continue, if you're liking the video, maybe hit the thumbs up. And if you haven't subscribed yet, consider hitting the subscribe button as well. It really helps us out. Okay, so far we've shown that t is less than 2p. And now we're going to break this into cases. So the first case is if p divides t. In other words, t is a multiple of p. Notice that t is a natural number, but it's less than 2p. The only multiple of p, which is a natural number, and less than 2p is p itself. So this immediately leads to t being equal to p, like I just said. But now let's throw that into our previous equation for x times y. So actually, while we're at it, let's get that equation for x times y back on the board up here, because we're going to use it a few times. And that's x times y is t cubed minus p squared all over 3t plus p. Now we'll take our t equals p and plug it into that and see where that leaves us. So we have x times y is now going to be t cubed minus p squared. So that's p cubed minus p squared all over, well, that's going to be 3p plus p, in other words, 4p. But now observe that some things cancel here. This actually cancels all the way down to p times p minus 1 over 4. Now let's observe the following, and this is a little bit tricky. And so that means that x and y are solutions to the following quadratic equation. And that quadratic equation is u minus x times u minus y equals 0. That's pretty clear, right? Now we can multiply that out and we'll get u squared minus x plus y times u, and then plus x times y. But then simplifying, this is u squared minus x plus y, but x plus y is t, which is equal to p in this case. So minus p times u plus x times y, which we calculated to be p times p minus 1 over 4. So check it out. We've got this quadratic equation where p is like a parameter or something. Now we can solve this quadratic equation and we'll get the roots of it, which are x and y. But we can solve just... And now we'll solve this quadratic equation using the quadratic formula, and we'll have x and y. So that means x and y is equal to, so it'll be p plus minus the square root of, let's see, we'll have p squared minus 4 times a times c, if you will, which is minus p times p minus 1 all over 2. But then simplifying, that's p squared plus minus. Observe that this term in the radical simplifies down to p over 2. But the square root of p is, well, it's never going to be a natural number. In fact, it's never going to be a rational number. So this is not a natural number. But x and y had to be natural numbers by our assumption up here. So, well, what does that mean? Well, that means that we, in fact, don't have a solution where t is equal to p. So I'll just maybe put like an x here to mean that there's no solution down this case, which means we need to move on to the next case when p does not divide t. So let's do that. Okay, so our second case, like I said before, is when p does not divide t. We're going to use that expression for x, y over there. But I'd like to observe that we can view that as a polynomial in t over another polynomial in t. Observe that we've got a cubic polynomial over a linear polynomial. We can do polynomial long division to do a simplification of that. So let's notice that 3t plus p can divide into t cubed minus p squared. So let's see how we would do that. So in order to achieve t cubed out of this, we need to multiply by 1/3 t squared. So that's going to give us t cubed, and then plus 1/3 t squared times p. And then let's recall the rules of polynomial long division mean that we group that and subtract. So that means down here we're going to have a minus 1/3 t squared times p minus p squared. Now in order to achieve this minus third t squared p out of this, we need to multiply by minus, let's see, it's going to be 1 over 9 and then times t times p. So let's see, now that's going to give us minus 1/3 t squared p, and then it'll be minus 1/9 tp squared. And then, well, canceling or grouping and then subtracting, so that'll give us 1/9 tp squared minus p squared. And then, well, there is in fact one more step of that, but maybe I'll leave one last step of this polynomial long division as a homework exercise, and that allows us to rewrite xy as follows. Actually, we're going to write 27xy using this just because we're going to clear some denominators. So let's observe that 27xy, when all is said and done, is 9 times t squared. That's in fact what we get by multiplying this by 27. And then it'll be minus 3 times t times p. That's multiplying this by 27. And then the term that we left off will be plus p squared. And then we'll have a remainder. And then the remainder will be over this thing that we're dividing by, this 3t plus p. So let's see, the remainder will be p squared times p plus 27. And then, like I said, this is over our 3t plus p, 3t plus p. But now let's observe that a bunch of this stuff is inside of the integers. So observe that this term is an integer. This combination right here is also an integer. So those two facts imply that what's left over is an integer. In other words, p squared times p plus 27 all over 3t plus p is an integer. Now, next up, we know that 3t plus p is not a multiple of p. It's not a multiple of p because of this fact right here. So that means it can't divide p squared. But since it can't divide p squared, it has to divide p plus 27 in order to achieve an integer right there. So we have 3t plus p divides p plus 27. Now what we can do is essentially subtract 3t plus p from both of these. And that's because, well, notice that p plus 27 is a multiple of 3t plus p. That means if you subtract another multiple of 3t plus p, then it's still a multiple of 3t plus p. So that's going to give us the following. So 3t plus p divides, so subtracting a 3t plus p from this will give us a 27 minus 3 times t. So we're at that point right there. Okay, then actually, let's start back at that point at the top of the next board and see where it takes us. Okay, so in our case, when p does not divide t, we got down to this 3t plus p divides 27 minus 3t. Now we're going to break this into subcases. So our first subcase is this object right here is non-zero, which occurs exactly when t is not equal to 9. So that means we've got a positive number dividing an integer. But if you have a positive number dividing an integer, that gives you some sort of idea of their size. So a positive number can only divide an integer if its absolute value is less than the absolute value of the integer. In other words, we have 3t plus p is less than or equal to the absolute value of 3t minus 27. I changed the order of that because I have the absolute value. And now an inequality involving an absolute value like this can split into two statements. They are OR statements. So in fact, we have 3t plus p is less than or equal to 3t minus 27, or we have 3t minus 27 is less than or equal to minus 3t minus p. So again, one of them involves negating and then switching the direction of the inequality. And the other one involves just like taking off the inequality. Okay, so let's see. This one right here gives us p less than or equal to negative 27, which clearly doesn't work. There are no primes, which are natural numbers, that are less than or equal to negative 27. I guess I didn't put up here that p has to be positive, but it does. Then let's see what we get here. So this is going to give us 6t is less than or equal to 27 minus p. But 27 minus p, if you run through the primes, keeping in mind that you want to achieve a natural number, this all has to be less than or equal to 24. You might say, well, why not less than or equal to 25? Because it's also a multiple of 6. So it's got to be a multiple of 6, which means we'll have 24. But that gives us some values of t. It could be 1, 2, 3, or 4. Those are the only ones that will achieve 6t less than or equal to 24. And now the goal is just to work these one at a time. And you'll see that working these one at a time gives you no solution for each. So for example, if t equals 1, we immediately have no solution. And that's because t is equal to x plus y, and those are both natural numbers. You can't achieve a 1 like that. And then what if we have t equal to 2? Well, that means that x plus y is equal to 2, which means that x equals y equals 1. But then plugging x equals y equals 1 into perhaps this equation right here, we will have 1 equals, well, t cubed minus p squared, but that's going to be 8 minus p squared over, well, 3t plus p, but that's going to be 6 plus p, or p plus 6. But then that's going to give us this equation, p plus 6 equals 8 minus p squared. And then you can check that that doesn't have a solution that's a prime number. So what do we have? We have p squared, and then plus p minus 2 equals 0. Which, observe, that's going to give us like p plus 2 times p minus 1 equals 0, which means p is either -2 or +1. Neither we're letting be prime numbers in this setting. And then, well, you can check the other two cases on your own will not lead to solutions. So, since when t is not equal to 9 does not lead to a solution, that means t must be equal to 9 in order to get a solution. So let's look at those. We boiled this all down to a single last case, which is the case when t is 9, or x plus y is 9. We also know x times y is that object over there. But let's calculate that. Observe that x times y, so that's going to be t cubed minus p squared. So t is 9, so that's going to be 9 cubed minus p squared over, let's see, 3 times t, so that's going to be 27, or 3 cubed plus p. So I've written it like this because there's a trick of factorization we can do. Observe that this 9 cubed is in fact the same thing as 3 cubed squared minus p squared. That's what we have left over. And then here we have 3 cubed plus p. But now observe that that numerator will factor as 3 cubed minus p squared times, or 3 cubed minus p times 3 cubed plus p. And then that's all over a 3 cubed plus p. Now we get this 3 cubed plus p canceling, and we have x times y is in fact equal to 27 minus a prime. And now from here we just go case by case. So notice that if we have x plus y equals 9, we can have the following possibilities for x and y. And of course, we can swap them as well because we've got symmetry built into this. We could have x equal to 1, y equal to 8, 2, 7, 3, 6, and then 4 and 5. But let's observe that if we have x equal to 1, y equal to 8, we have xy equal to 8. But 8 is in fact equal to 27 minus 19. So that tells us that p is equal to 19, and we have a solution. So let's maybe gather a solution right here. We have x equal to 1, y equal to 8, p equal to 19, and then we also have x equal to 8, y equal to 1, p equal to 19. That's the other like symmetric solution that we've just grabbed. Now let's look at this next one, x equal 2, y equal 7. So notice that's going to give us xy equal 14. But if xy equals 14, 14 is equal to 27 minus 13, which tells us that p is equal to 13. And we've got a set of solutions for that. So you could write that set of solutions just like we wrote the other one, but let's not do that. And then we have x equal to 3, y equal to 6, which will give us xy equal to 18. But observe that 18 is 27 minus 9, but of course 9 is not a prime number, so this does not give us a solution. And now, just for good measure, let's take this last case and leave it as a homework exercise for you to determine if that gives us a solution. Maybe post in the comments if it does or not, and that's a good place to stop.